Hi geometry folks. So we're continuing in our unit 4 now. We're moving on to investigation 2. Today we're going to do lessons 1 and 2 starting on page 78 in our workbook. All right, so we're going to be working with right triangles. And so on page 78 at the top you can see that we have a right triangle, ABD. Okay. Big triangle A, B, D. And it's actually made up of two smaller triangles. Okay, so ABD is our big triangle. And triangles, right triangles, are triangles that have a 90-degree angle or a right angle. 90-degree angles are called right angles. And we're specifically working with right triangles right now. Okay, so we have a right angle here. And we have another right angle here. We have two triangles back to back here. Okay, so we have triangle ABC, which is the bigger one on the right, and it's kind of standing back to back with another right triangle, ADC, here. And so their right angles are kind of back to back with each other. They're supplementary, forming that right, that straight angle here. So in triangle ABC, the bigger one on the right, the pink one, the hypotenuse is side AB. The hypotenuse is the slanty side, okay? Every right triangle has two legs, and the legs form the right angle. Think about legs making an L shape where the right angle is. In the other triangle, ADC, these are the legs forming the right angle, and side AD is the hypotenuse. Okay. In that triangle, ADC, the green one over here on the left, DC we would call the short leg, right? Of the two legs, one is shorter, one is longer. AC is the long leg. And we're going to call the parts of the right triangle that. We're going to call them the short and the long legs and the hypotenuse. Okay, so let's look at triangle ABD, the whole big one, okay? This segment AC that starts at point A, vertex A, and drops down to a right angle, it forms a perpendicular line to that other side, okay? So segment AC is called the altitude, okay? It starts at vertex A, which is a point, and it's perpendicular. That means a right angle to side BD along the bottom, okay? So an altitude is a line in the right in a triangle that starts at one point and it comes down at a right angle to the opposite side, and it cuts that triangle into two smaller triangles. That's what we're going to be talking about in today's lesson. Cool things happen when you do them. All right, so we're moving on to page 79, and we're going to talk about what happens when you draw an altitude in a triangle. So here we have a big triangle ABC. I'll make this one be pink color. And we're dropping an altitude from point B. And we're going to go down like this and make it be at a right angle to the other side. Okay, and it cuts it into two other triangles. So this is also going to be a 90-degree angle, right? Because together they make 180. So we have a triangle here, ABD. Okay. And we have another triangle on the other side here, which is BCD, BDC, right? And we have the big triangle. All right, and we'll call that one ABC, the big one. Okay, so we have three triangles. We have triangle ABC. That's our big pink one. All right. We have triangle BCD, BCD, and that will be our green one. in color coding. And, whoops, there you go. And we have triangle ABD, which is the smaller purple one on the bottom there. All right. So here's something really interesting that happens, you guys, when you draw these altitudes and cut a triangle into two more triangles. Do you remember when we talked in the last lesson about the rules for how we know triangles are similar? Do you remember one of the rules was angle, angle? If two triangles have two pairs of congruent angles, then those triangles are similar. They're the same shaped triangle, just different sizes. So listen, they're asking, is ABC, triangle ABC, similar to triangle BDC? So they're asking ABC, the big pink one, is that similar to BDC, the green one? Well, look at what we have here. In ABC, there's a right angle down here at the bottom, right? In triangle BDC, there's a right angle right here at point D, right? So that's one pair. They both have a 90-degree angle. But look at both the pink and the green triangles also have an angle C. That's in both triangles, okay? So yes, because of angle, angle, we know that ABC, the big one, is similar to BDC, the green one. We can do exactly the same logic with the other question. How about big triangle ABC and purple triangle ADB? Well, again, big triangle ABC has a right angle. Small purple triangle ADB has a right angle here. And both of them have angle A. So again, they both have angle, angle, saying that they must be similar triangles. So you guys, we also had a rule from a couple of units ago called the transitive property. If you remember the transitive property, this is how it's going to work in this case. The purple triangle is similar to the pink triangle, right? Because of angle, angle. But the pink triangle, we said, was similar to the green triangle, right? And that means that the purple triangle has to be similar to the green triangle. And this is a typo. That should be ADB, okay? But that basically means, you guys, all three of the triangles are the same shape. They're all similar to each other. That is an incredibly cool thing to know because we can solve some interesting problems using that idea. Okay? So we're going to, right now, we're going to solve a problem. You'll see how cool this is. All right. So that is actually called a similarity theorem. That's called the right triangle similarity theorem. That if you draw an altitude to the hypotenuse of a right triangle, then the two triangles that you form, the two smaller triangles, are going to be similar to the original big triangle, and they're going to be similar to each other. So let's do a problem on page 87, and you'll see how easy that is to work with. Okay, so here we have at the top of page 87, we have a big triangle ABD, and we've drawn an altitude from vertex D to the hypotenuse here. It's a right angle, okay, and it's forming two smaller triangles, and we're only going to be looking at these smaller ones right now. We're not even interested in the big one right now, just the two smaller ones. And we know they're similar to each other, right? We just proved that. We did that whole angle business, and we proved that they're similar. Okay, so let's think about what parts we have here. All right, so in any triangle, any right triangle, they're both right angles, we're going to have one longer leg and one shorter leg. So in the pink triangle, we need a short leg and we need a long leg. Okay, this side that's 4 units long is our short leg. This side, which is X units long, that's our long leg. But look at the green triangle. We need a short leg and a long leg here also, right? In the green triangle, it's the X that's the short leg. and it's the 9, that's the long leg, right? If it's hard to see that, all we have to do is cover up one of the triangles. If you're only looking at the pink triangle, the 4 is the shorter leg, and the X is the longer leg. If you're only looking at the green triangle, the X is the shorter leg, and the 9 is the longer leg, right? Okay, in the last lesson with similar triangles, we talked about scale factors and proportions. So let's calculate those. You know, if triangles are similar, their scale factors have to be the same, right? So we know that if we compare the short leg to the short leg, that scale factor has to be the same as if we compare the long leg to the long leg, right? So let's put the short leg numbers on the top, the pink triangle numbers on the top, and let's put the bigger green triangle numbers on the bottom of the fractions, okay? So pink triangle, the short side is 4, the longer side is X. We don't know what X is. That's the question. We have to find out how long it is. In the bigger green triangle, the X is our shorter leg. Yeah. Okay. In the pink triangle, the X is the long side. In the green triangle, the 9 is the long side. So here's our proportion. 4 divided by X equals X divided by 9. We solve by cross-multiplying, right? Multiply both sides times 9. Multiply both sides times X. And you get 36, 9 times 4 equals X squared. Last step, we don't want X squared, so you square both sides, square root both sides, and we get 6 equals X. So now we know that this side X is exactly 6 units long. The comparison of 4 to 6 is the same as the comparison of 6 to 9. Okay? You're going to see a problem just like that in your whiteboard chat, and you're going to see another problem just like that in your exit ticket. So if you need to replay that one, go ahead and do that. All right, also talking about right triangles, there's one more thing that you have seen before, and we're going to talk about it now. On page 93, we're going to talk about the Pythagorean Theorem, which is a squared plus b squared equals c squared. You probably remember that. A and b are the legs, c is the hypotenuse. So that's saying leg squared plus the other leg squared equals the hypotenuse squared. C is always the hypotenuse. Doesn't matter which number you're missing, c is always the hypotenuse, okay? So here's a question, here's a problem. We've got some city blocks here. Elm Street, Maple Street, and Washington Avenue. Elm Street and Maple Street form a perfect 90-degree angle where they meet. Elm Street is 120 meters from this point to this point. Maple Street is 400 meters from this point to this point. So if we wanted to walk from this point all the way around to point K, we would have to go 120 and 400, which is 520 meters, right? But we could take a shortcut. We could just go along Washington Avenue and go straight from this point to this point, which is the hypotenuse of this right triangle. This piece, this hypotenuse, is going to be shorter, right? You can tell that that's shorter than going around the long way, but let's see how much shorter it is. If we use the Pythagorean Theorem, we know A is 120, square it. We know B is 400, square it. And we're going to add those numbers together, and that's c squared. Well, you guys, a squared, 120 squared, I've used my calculator, and that is 14,400. And 400 squared is 160,000. If you're using a calculator or doing it by hand, watch out for your zeros, okay? It's easy to forget one. Then you mess up your calculation. If you add those together, it's 174,400 equals c squared. Do not forget, this is c squared. This is not c. You must square root both sides. That is a common mistake. C, when you square root 174, 400, is 417.6 meters. That is much shorter than 420. Let's see how much shorter it is. You just subtract. And if you subtract 520 minus 417.6, you have saved yourself walking 102.4 meters. Okay? So if you're not a person that likes to walk, you saved yourself a lot of walking by cutting through the hypotenuse there. All right, second problem on this page. Looks crazy complicated, but no, it's not. It's just the Pythagorean. We're just going to do it a few times, okay? They want us to find how long this side x is. And they've given us this really interesting diagram where we have three different triangles. We know this side and this side are 10 feet long. We know this side and this side are also 10 feet long, okay? Let's just start with this right triangle. We know 10 squared plus 10 squared. Let's see if that's x. I'll call this y and I'll call this z. Okay. We know 10 squared plus 10 squared, a squared plus b squared, must equal z squared. Just looking at this pink triangle, right? So that's 100 plus 100. Add them is 200 equals z squared, square root them, and z equals 14.1, rounded, okay? So we know that. We know this is now 14.1. All right, let's move on to the next triangle now. We know this leg is 10. Now we know this leg is 14.1. We do the same thing again. So we're going to say 10 squared plus 14.1 squared equals, now the hypotenuse is y, right? 100 plus, we know 14.1 squared is 200 because we just came from that. 300 equals y squared, square root both sides, and your y is about 17.3 if you round. Okay, now we are at the final stretch here, folks. Here's our last triangle. We know this side is 10. Now we know this side is 17.3, and we do our final calculation. 10 squared plus 17.3 squared equals x squared. That's the one we want to know. Finally there. 100 plus 17.3 squared was 300. Add them. Got a square root because we don't want x squared. We want x. And x is 20. Finished. There's our final answer. All right? So that's the Pythagorean and the Pythagorean and the Pythagorean. And we're all done, and you can go back and do your whiteboard chat now.